Hi everyone, continuing with our energy lessons. Let's see what all we have covered. Quick recap. Um, we covered what is energy, what are different types of energies, like at a high level, kinetic potential. We saw thermal energy transfer basically. We saw that the in different, like it's called conduction in solid, convection in liquid and gas, radiation when a matter is not involved. So after that, today we will see some examples of energy transfer. We'll also understand transformation. So energy never gets destroyed. Okay, so it just transfer from one energy to it transfer means one energy to the same kind of energy, and transform it energy can also get transformed, which means it becomes from one form to another form, right? So we'll see some example to understand that better. So let's see our slides and then I'll come back to the sketching part of it. Okay. So we will cover all these. We will also see a special diagram, Sankey diagram, which shows, which indicates this, which we can use to visualize how energy transfer and transformation is taking place and see the efficiency of devices. Okay, we will understand when we go a little deeper there. Cool. And we will understand what is energy efficiency basically. When we say some device is energy efficient versus another device, what does it even mean? Okay. So before that, see energy from sun, all the energy that comes on earth comes from sun. Okay. So how does it come? With this is also kind of transfer, yes, that heat, light is transferred, this kind of energy is transferred from sun to earth. Okay, so sun gives off light and heat energy, right? We all know that you feel hot and you can see the light during the day. During the night also you see sunlight via moon. That's for some other day, but you already know that from year seven. Okay, this energy is produced by nuclear reactions that are happening in sun's core. Okay, so it this reaction is mainly nuclear fission, but we'll learn about that later. And what is happening is that nuclear potential energy, which we saw in first lesson, this nuclear potential energy, which is happening on sun due to nuclear fission, is getting converted into, which means transformed into light and heat. Then the sun radiates this energy, so there is no in space we know it's mostly vacuum, right? So there is no matter with using which this energy comes to earth. It's basically radiated. We learned about conduction, convection, radiation in the previous class. So the sun radiates this energy into space in all directions, and a small amount reaches earth. Okay, so you can see one energy transfer happen in this case using radiation. um So what is energy transfer? Okay, so energy transfer is basically is energy moving from one object to another. So in this picture, you can see that there is this heat energy, thermal energy, right? Because there is a gas or maybe electric oven. But let's take gas. Actually, you can take anything. But we are talking about thermal energy here right now. Um, so you see it gets transferred to this pan first, right? It becomes hot. And then eventually it transfers to this egg where this dish is being made. So this heat gets transferred from uh, like bottom to the frying pan to the egg. So energy moves from one object to another, producing observable change. And you can see your dish being prepared, a good smell coming out of it, and looking change is happening, right? You can observe that change. So that is energy transfer, basically energy moving from one object to another, producing an observable change. Let's see another example. Okay, so this example is basically energy transformation. Here now, energy transformation means that one form of energy changes into another form and causing change in the system. So again, both energies are causing changes. That was our initial definition of energy, if you remember from lesson one. Um, okay, so energy transformation here, what is the transformation? So there is a electric energy, like from the switches, and it's getting converted into light and heat, right? The bulb, if you keep it on, it will become hot and also emit light. So that is like electrical energy converted into two different kinds of energy. And because there is a, in the previous case, the thermal energy, heat energy was remained heat only, right? It was transfer. Here, electrical energy become a different kind of energy, light and heat. So it's transformation, right? Um, so transfer moves the same energy from place to place in case of egg frying. And transformation changes energy from one form to another. Cool. Let's see some more transformations. Cool. Okay. So let's say there is a person, and this is a person, and they have eaten some food. Okay. So that's how they get energy, right? So food is basically what? So let's say this is apple. This is like food is chemical, right? I mean, they are molecules and related to chemistry that way. So this food actually contains chemical potential energy, right? It's one of the subtypes of uh, subtype of potential energy. Okay, so chemical potential energy is in fruit, which is now stored in your body. Let's say this person's body, and then this person decides to throw a maybe a heavy object, let's say a stone. Okay, so this person has an arm, a beautiful arm here out. Okay, holds the stone and swings this arm. So when the arm moves, when there is a movement, it's called kinetic energy, right? So there, this chemical potential energy, because this person got a strength now, decides to throw a ball, I mean a stone, and this chemical potential energy transformed because see, chemical potential energy is a different kind of energy, and kinetic energy, I'll just use Ke, is a different energy, right? So transformation. So transform the arm is moving. Okay. And what happens then? This stone comes at a certain height here and gets released. Okay. So the stone is released. Now, this kinetic energy in the hand is transferred to the stone's kinetic energy, right? So stone will eventually come somewhere, right? So let's say this is the same stone coming down. Okay. And so your kinetic energy got transferred to kinetic energy here because still there is a movement, right? So this is transfer. The previous one was transform. Cool. So now this stone has certain height because of its like its position above the earth. And we know that there is a gravitational potential energy when an object is held above, right? From our previous lessons. So gravitational potential energy. So there is again a transformation. And there is this, then this gravitational potential energy also gets converted into kinetic energy because this stone is moving and eventually it will come down and maybe let's say it makes a sound. So then this kinetic energy also gets converted into a sound energy. So which is a transformation. So sound energy, right? So you can see a lot of transfer and transformations happening. So that's how energy takes different form or gets transferred but never lost. Okay. Um, let's take one more example, maybe just to like solidify our concept. Um, let's see what example can we take. Okay, we ride cycle. Generally, everyone rides cycle. Okay, so let me make a good cycle. Yeah, this is the basic diagram, and then let's say there's a pedal over here. Cool. and then another wheel. Okay. So now here, let's say we are sitting. Okay. This person is sitting and they are pedaling. Now they again eat food, so they have chemical potential energy because of food. Then they move their legs up and down the pedal. Movement means kinetic energy. So there is a kinetic energy being applied to the pedal, and this kinetic energy is then transferred to the wheel, right? So the wheel moves. So kinetic energy is input, and another kinetic energy to the wheel is output, right? And the cycle moves. Cool. And you would see that because of the movement, there is a little sound. Cycle makes generally a sound, which is sound energy. And if you would touch, there will be a little heat also generated wherever the parts are uh, colliding with each other. So it also generates that heat energy. Okay, and sound energy. So this is transformation. So kinetic energy in, kinetic energy out, and then also sound and energy, heat energy out. So you can already see some kind of flow, energy going in, energy going out, and you are also seeing some kind of, I mean, transfers and transformation. So this is another example of transfer and transformation. Okay, let's move back to our presentation a little. Um, right. So then what is efficiency? So when you on a bulb, what are you most interested in? You're interested in the light from the bulb. You are not interested in heat, which is coming out of the bulb, right? We have on the bulb, we want light. But what happens? Heat also comes out. But we don't, our intention is I want to maximize light. I want light, not heat. So heat is wasted energy in this particular case. And light is what I wanted in this particular case. So light is the useful energy. So efficiency means how much useful energy is transferred or transformed during a change. So the more light it will give and less heat it will give, that is more efficient, right? Because in this particular case, I want light. If you give me more light, I will buy you. If you give me less light and more heat, that heat is waste in this particular case. So energy efficiency is a measure of how much useful energy is transferred or transformed. Cool. So that is energy efficiency. Okay, using a higher share of input energy basically for useful output and minimizing waste. So if you have to define it in proper words. So efficient devices, high useful energy output, little energy wasted. And inefficient devices, low useful energy output, a high share is wasted. So here you can see these are new kinds of bulb. Maybe you have only seen these kind of bulbs, but maybe somewhere in your house you may have old kind of bulb also where you can see a filament. Um, and maybe it's more kind of transparent also. You can try to find somewhere and maybe think about replacing it with a LED bulb because LED bulbs are more efficient. Why? Because they emit less heat. From bulb, we want light, right? For the same amount of input, which is electricity, we want more output in terms of light and not heat. But in case of filament-based bulb, more output of heat also comes, and that is a wasted energy. Okay. So it's less efficient like devices. Device is something which can be used to transfer or transform energy or to do work that way, right? From our definition of energy. Um, okay, so that defines what is efficient device, a high useful energy, a device which gives a high useful energy output and which wastes less energy. Cool. So Sankey, so we earlier saw that energy is coming as input and then energy is going as output, either it's getting transferred or transformed. So Sankey diagram actually shows this visually. Okay. That what is energy in and what is energy out. Now we know units, yes, in science there is always unit like kilogram or Newton for force, kilogram for mass. and then let's say kilometer is like, so is a unit, right? So for energy, when you have to measure energy, one of the popular unit is joules, denoted by J. Okay? And we will see Sankey diagram showing energy input in joules, energy output in joules shortly. Cool. So what is Sankey diagram? So let me draw it first for you. Okay. So let me go back to my good drawing board and let me move here. And I want to make it accurate, so I have to refer to my notes as well. Okay. Um, right. So let's make a Sankey diagram for LED and LED bulb and filament based bulb. Okay. So let's say this is LED here. Okay. And let's say this is filament bulb. Cool. Yeah, you can see, right? So in Sankey diagram, we make basically some arrows like a flow. So we say that initially, let's say this is the energy. Okay, so this bar, its height, it indicates that, let's say we say 100 joules of electricity is being provided to it, electrical energy is input. Okay, so this LED is plugged, this filament is plugged, and same we will provide to filament bulb also, 100 joules. Okay, this is energy in. So this diagram is showing that energy in is 100. Okay, now what does a bulb emit? We said that bulb emits light. So we indicate, let's say, a light that coming out of this input, and it also emits heat. Okay, so let me just rub it a little bit. Let's draw the filament one first. Okay, so yeah, so the output basically is heat, no, sorry, light, which we are interested in. And this is, let's say, so light energy here is, let's say, 20 joules. Okay. J is for joules, the unit. Okay. And then filament bulb also emits heat, right? So in filament bulb, the heat is really a lot more than light. Okay. So that's why I'm making it fatter, like this in Sankey diagram. And actually, the total width shouldn't exceed the total input. Yes. So because this width denotes maybe this one. So there is a heat energy basically. So how much heat energy will be there? Has to be 80 joules, right? Energy is not lost. Energy is just transferred. So 100 is here input and 100 is output. But you can see only light energy 20 came out where we give 100 joules. So means this is useful energy from bulb. We want light. So this is useful energy. So this filament bulb is not um, that useful because it's giving for the input, it's giving less output in terms of useful output. Now in LED, the light is more for the same amount of input. So let's say here in this particular case, let's say it's 70 joules in light, and there is always a heat also. Okay, so the heat is, let's say, 30 joules, has to be 30 joules because it's not lost, right? So this is heat energy. We are labeling also, so you must label your diagram. Okay, but always make sure that input is equal to output. So 70 plus 30 is 100. Okay, otherwise your diagram will be wrong. And then see the width also in the top, like 70 and 30, there is a proper ratio I've tried to maintain. So if you draw with hand, maybe you can keep the same ratio like 70 to 30, and then you can see the 20 line is significantly less width than 80. And then so if, let's say, I will make a wrong kind of diagram which will explain you what a wrong looks like. So let's say if I make 100 this, and then if I make, let's say, this even like so fat, like which is looking more like 100, and then I call 80, this is like a wrong kind of drawing. Yeah, label may be correct, but drawing is not that good. And let's say I make a even fatter light, energy, and then I say it's 20. So it doesn't look good because the width is not matching. So this is a wrong example, okay? These are kind of right. Maybe you have even better writing than me and better drawing than me, so you will be able to make better diagrams. But you got the idea, right? A Sankey diagram should show input, output, like the types of energy. So here you should say electrical energy going in, electrical energy in, and then two kinds of energy out and their amount, and the width of the arrows indicate how much. I mean, they have to be in proportion. So Sankey diagram shows that. Cool. So if someone asks you that using Sankey diagram show that LED bulb is more efficient, so then you can show like this. You can make this diagram and explain this diagram that input is this, output is this. So the output of light is more in for the same amount of input, and that's why LED is more efficient. Cool. Um, let's then move on. Maybe let's go to presentation slightly. Then we'll come back to our drawing. Okay, so what is Sankey diagram? A flow diagram because it shows the flow of energy, yes, from input to output. Okay, the flow diagram where arrow width is proportional to quantity of energy in this case. Okay, the Sankey diagram is for energy here. You can use Sankey diagram for other things also where there is input and output. Then energy conservation, the total input equals total outputs across all branches. We saw, right, 100 and 70 plus 30 and 80 plus 20. And output split into useful work and losses. Cool. So useful energy and loss energy where we are not interested in that energy. Okay. So similarly in a fan, if you have to draw a Sankey diagram of a fan, let's quickly do that also. Okay. So this was for LED. Let's go here. And a fan takes electrical energy, right? And fan, you plug it into electricity. Let's say, so input is electrical energy. Okay. And let's say the electrical energy is around 400 joules. Okay. Fan needs more energy than a bulb. You can already make it out, right? Uh, okay. So this is input shown. Then, so this is for fan. Let's label it like that. Fan Sankey diagram. Sankey diagram. Okay. Okay. Sorry for the bad writing, but you are getting, I hope. So now fan, when you on it, it moves, right? That fan rotor moves. So movement means kinetic energy. And that's what we want. Yes, when it moves, it gives us air. So that's useful energy then. So let's say this fan gives us 80 joules of kinetic energy, which is what we want. So this is kinetic energy. Okay. But what else fan gives which we don't want? One is sound. Your fan makes sound, my fan makes sound. But it doesn't make a horrible sound. So I'll keep it thinner. Okay. So let's say it gives me some sound energy. And as the width is lower, so I shouldn't make it more than 80. Yes, let's call it maybe 20 joules of sound energy. And you would also see fan becomes hotter, like its motor becomes hot. Some fans also have grills to dissipate that heat. So that's the wasted energy because we really don't want that energy. So, yep, so that is the wasted energy. Now, see, the cleverness I have done is that I made this diagram like this so that this plus this will be 400 joules. So this way I won't exceed or fail, right? Okay. So this is thermal energy, which we don't really want from a fan, yes. So thermal energy is also wasted energy. And this has to be 300 joules, right? It all have to add up to 400. 300 plus 80 plus 20 will be 400 joules. So that is showing us, and efficiency is, this is the amount of useful energy, 80 joules out of 400 joules. So my is not so efficient. Yes, I'm losing so much of my input in waste energies. Cool. So that is Sankey diagram. That's what Sankey diagram shows. All right. Cool. So, yep, in the fan, electrical energy goes in. Useful energy is the kinetic energy. Waste energy is the sound energy. Waste energy is the heat energy, right? Heat energy is happening because of friction. Okay. In this particular case, we did this, so I won't go into LED and filament. Now let's take one last example of car. You would be very interested in car, I assume. Okay, let me make my diagram quickly. These all example, you may say that, yeah, you get Sankey diagram, you don't want so many example, but maybe they reinforces our learning, and car is an interesting topic. So this is the last example, okay? Now car would really need a lot of energy. Now, which kind of energy a car takes? Till the time I draw it, you can say fuel, but I want the answer from my first lesson, like, is it potential energy? Is it kinetic energy that it takes? And if it is potential energy, then which potential? Is it gravitational potential energy? If not, then what energy? Yep, it takes petrol is a chemical, right? So let's say petrol energy is what it is taking. Okay. And now instead of using that joule, I mean, I can use, let's say it's 100% input of potential energy. I mean, chemical potential energy, petrol energy. Okay. 100% is the input. If I'm giving input in percentage, my output will also be percentage so that it makes sense. Okay. Otherwise, you give input as percentage and output as joules, the diagram doesn't look good. It's not easy. Then person has to convert themselves. Okay. So from car, what do you want? Apart from comfort, you want speed, right? You want to go somewhere with a car. So when you want to move with a car, it's kinetic energy. So that is the useful energy that comes out. So I will use my old trick of making my diagram at least proportional, right? Hope you are getting that trick. So this is kinetic energy. Kinetic energy and energy, let's say this is 25%. Okay. So this is the kinetic energy. Now you will say that why should I make how should I decide it is 25 or not? As long as you can understand that there some you have to keep as waste and some you have to keep it useful, you can vary these percentages. Now from general knowledge, you can see that in a car there is a lot of heat. Like you would have seen those old movies where the old broken car on a bridge has a bonnet on and the heat is coming out, like the smoke is coming out. It's the heated engine. So there is a lot of heat waste in a car. And you would have seen exhaust fans from which these like sound also comes. So sound energy escapes and some heat also escapes. So and in if you really like cars, you would know there is a coolant in the engine, like at least in old cars. I don't know about the electrical cars these days. You would know better. But there was a coolant and which so most work like most things in car, like most kind of energy in car actually is to manage the temperature within the engine. Okay. So that's a lot of waste in a car. Okay. So based on like your situation, you can make up these numbers. Just keep them reasonable. Yes. Uh, unless we get a super efficient car, maybe it will be 80% kinetic energy. Okay. So, but nothing is wrong as long as input and output matches. Okay. And it's reasonable. Cool. So, yep. So then there are, so what happens when petrol is put in the car and you ignite it? Yes. I mean, you start your car. In that case, like this petrol creates a lot of gases, hot gases, which so this is chemical potential energy. Let's me call it chemical let me just call it chemical energy. You would know chemical potential energy, we chemical PE. Okay. And it moves the pistons, which you don't need to worry about. They go up and down um, in your car. And when they go up and down, that if it is moving, it's like kinetic energy. So chemical potential energy is converted into kinetic potential energy, which you don't need to make in this Sankey diagram. I'm just showing you kinetic energy is there. Then it goes to gearbox. Also don't need to make in Sankey diagram. I'm just explaining what's happening a little high level in a car, right? And then so this kinetic energy goes to gearbox and then finally transferred to the wheel. Okay, so kinetic energy, this potential energy becomes kinetic energy, and this is that kinetic energy coming out, which is making your car move. But as engine is, these are going up and down, there is a lot of friction being generated and there is some noise. So let's make a noise, but hopefully the cars are not these much noisy. So let's say this noise is maybe 2%. Okay. And then in exhaust also some heat escapes, so which is actually a lot of some cars have two exhausts. Okay, so let's say this is 20% going on. Okay, some heat is radiated from front. I mean, if you've seen old cars, some you will feel actually in the top of bonnet there is a lot of heat coming out. So some heat is radiated also. So some energy goes there. Let's say maybe 8%. Okay, and then a lot of heat is into. Now, see, I didn't follow my diagram properly, so I will have to now balance it. So let's say I didn't use my trick properly. I should have done like this. Okay, let's correct it. Then like this, then like this. So I have left this much. Okay, so let me make it a heat energy. So this is heat energy waste, and I didn't label them. So see, that's why if you don't label it, no one knows what you're doing. Okay, so this is noise, 2% noise, and this is exhaust. Let me move it a little up. Exhaust. All of these are basically only managing the heat. This is radiated energy, and this is, let's say, heat energy, which is going in like managing the heat of engine. It's all inside. Okay. So heating, cooling. So let's say this goes in heating, cooling of the engine. Okay. So this Sankey diagram now, and this will be how much? So out of 100, we consumed how much? 20, 30, 55. So this will be 45% remaining. Yes. So 100% all. So when you add up 25, 45, 8, 2, and 20, 100 will come. So input has to be same as output, right? So that's our car Sankey diagram. It's not that efficient car, like, yes, only 25% output, which we really need. We don't want heating, cooling, we don't want noise, but it will always happen in machines. There will be something which will be lost in this transformation. They will be transferred. Okay. Lost doesn't mean it's destroyed, it's just converted, transformed into another energy. Okay. Right, there is one important thing in terms of energy transformation that we need to cover, and then we can call this as an end. Okay, that's one last thing. This chapter was really big. I'm just following one of the prominent books, and so that there is a course structure, and you also can match the studies that are going in your own school, and not that I just want to cover so much. Okay. Um. So, okay, let's do some slides quickly. Energy transformation in cars. We saw chemical potential energy going in. Petrol stores chemical energy, which is released during combustion, which is burning in the engine. Combustion produces hot gases, transferring thermal energy to the pistons or the parts of a engine. Okay, that make it work. So it produces hot gases, which then transfers this thermal energy to pistons, and then moving the pistons, which is kinetic energy, that is the thermal energy, into mechanical energy. Mechanical energy here is kinetic energy, moving those pistons up and down, spinning the engine and gearbox. Okay, and then finally kinetic energy in the wheels, which we discussed, right? And then energy transfer is like energy, kinetic energy from engine is passed to gearbox, to the wheels. We already discussed this. Significant energy is wasted as heat through the exhaust and engine. Additional energy runs cooling and heating systems. We discussed all this in the previous sketches. And friction in gears, tire load. So those were the transmission losses, which I probably didn't explain nicely, but this one says that I made some transmission losses in the diagram, if you remember, or if you go back in the video. This is because of the air resistance when the car is moving, friction in the gears, tire road contact is causing friction. Friction you learned in year 7 mostly. Um, okay, so those were the losses. So now you know very nicely what is energy efficiency, what is Sankey diagram, how to make Sankey diagram for fan, for car, for a person throwing a stone, and now you can LED filament, and you can make your own. So finally, we will come to an interesting thing like a pendulum. I don't know if you have seen a pendulum clock or not. I have seen one pendulum clock at my grandfather's place. I wish I would have kept that clock. I miss it. But yeah, so pendulum, what is a pendulum? You would have seen, I mean, if not seen, maybe you can take a string, tie a stone, and just move it like this is pendulum. Okay, if not a clock, it can. So any object, basically, pendulum doesn't have to be a clock. So pendulum is an object suspended at the, and why pendulum? Like pendulum, there will be some energy transformations which will happen. So will be good to for us to understand how a pendulum, like what are the energy transformations happening there. Okay. So a pendulum is an object suspended at the end of a string. You see, there is an end of a string. Sorry, here. So this is the object which is suspended, that swings back and forth. Yes, you push it and then it will keep going like this and this and this. Okay. So in this particular case, this is a simple ball attached to a string, and that string is attached to a pole. Okay. So that is pendulum, the definition of pendulum. Now I want to use my diagramming skills. It's easier to explain, okay, than going through the presentations. Okay. So let's see, you may disagree, but I think it will work. Okay, so this is a pendulum, and let's say we push it, it will go like this, then it will come back, then it will go here, come back, go here, come back, go here, come back, right? We can do it for next 30 minutes, but let's. So what is it? So if I have to make a diagram, let's say when it is up here, it has gravitational potential energy, right? The energy because of its position above the ground, the gravitational potential energy. If you want to recap all this definition, you can go to the previous lectures, okay? But it's the energy which an object stores. It's a potential energy because of its position above the ground. So this is maximum over here, okay? And when then this, so gravitational potential energy gets transferred to kinetic energy. See, now you know it's moving, right? Kinetic energy. So kinetic energy is coming, coming, coming. It will be maximum speed here. And then kinetic energy will start to reduce and will become zero here. So here we can, you could label it that side also, but it's like it's at rest object where kinetic energy is zero. So kinetic energy is zero here. And again, it has a gravitational potential energy at this point. It has gravitational potential energy here also because of its position above the earth, but this is like reducing. So gravitational potential is zero here. Not zero, I mean in respect to its minimum here. Okay. And kinetic energy is zero here because now object is not moving. Now it will go down, then kinetic energy again comes. Yes. So if I have to make it in a diagram, like this, and let's say, just want to explain. So maybe not the good diagram. I'm just trying to make the diagram which mimics the book. Okay, better let me refer to the book, okay? That's easier. Yeah. So this is what the book shows and is a good representation actually. That's why better to copy it than to. Okay. And then let's use another color. Cool. So it's showing two types of energy, this diagram. You will understand soon. So here, see, potential energy is the minimum. Okay. So this bottom part is showing potential energy increasing. See, this is the maximum potential energy here, increasing potential energy. And the top part is showing, see here, there is no kinetic energy, increase in kinetic energy. See, the kinetic energy is maximum here. Then kinetic energy start to reduce. So top part is kinetic energy, bottom part is potential energy. It's just showing the same thing which I explained, that potential energy is higher at the position which is higher above the ground, and then lower, 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 lower. At this point, it's the minimum, then higher, 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 higher. Similarly, kinetic energy, as I explained. Okay, so that's how a pendulum moves between two kinds of energy are being transformed: gravitational potential energy to kinetic energy to gravitational potential energy to kinetic energy to gravitational potential energy, and so on. So when will a pendulum stop? Will never, right? If it was in space, maybe never. But on Earth, or actually in space also, there is a condition when it can stop, but maybe let's not go there. So here you see when it is moving, this anything which moves faces few things. Not anything, maybe. Let's see. So there is a friction going on here in this particular dark spot, and that will make it a little hot. A little hot. Maybe you don't feel it. It's a little, still there is thermal energy loss. Okay. And then there will be some air resistance, like there is generally always air race uh, if it is not in space. So this air resistance will also cause it to slow down friction. Okay. And that's why it will come to an halt. And that's why a pendulum stops, because of all these forces which are keeping it going forever. Cool. So yep, just quick recap. Energy shifts between gravitational potential energy and kinetic energy throughout the swing. At point one, yeah, this diagram is not that clear. My diagram was much better. Um, yep, but you got it right. Potential energy, so maximum gravitational energy before the release. Potential energy converts into kinetic energy as it descends. Maximum kinetic energy. So if someone asks you in a question that describe the motion of a pendulum or why pendulum stops, then you can now be able to answer, right? So maximum kinetic energy, gravitational. So when it is at the lowest point, it has the maximum kinetic energy, and gravitational potential energy is minimal. I didn't say it's zero because it's still, even at the minimum, it is still facing that gravity pull, right? So, and it has certain positions, so potential energy is not zero. But kinetic energy is zero because at the top, because it stopped there for very milliseconds, maybe microsecond, but it stopped there. So that's why we say kinetic energy is zero there. Okay. And then kinetic energy comes back and so on, right? You understand? Okay. Why it eventually stops? Because it loses a little energy to the air resistance, and rubbing up becomes hot. This diagram is actually good. And yep, we are at the end. Please consider paying for the lecture. It takes a lot of effort. When you pay, I'll send you a PPT for today. I'll also send you some lesson notes for today's lesson. For example, it can help you answer longer answers. Like if someone says explain and draw Sankey diagram for energy transformations in a car, you will be able to explain it if you try to remember it. Now that you understand the concept, if you just do that extra effort of learning the answers, it like now when you read the answer, you'll be able to understand from the pictures you have drawn from your own understanding, and you can make a longer, meaningful write-up. Okay. All right. So that's all. Happy learning.